sacred institutions. Bedroom eyes, they call them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depth.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time. Today we're doing part 2 of our series on subatomic physics, how to conceal a hadron, particle physics and the Standard Model. So last episode I made all kinds of wild promises about getting to the Standard Model, and then we detoured into atomic physics more generally, because I wanted to make sure we were all on the same page. So this episode sort of follows on from that, but you can listen to it as a standalone show. I'll start with the particles that make up the atom, protons, neutrons and electrons, and move from there. But as we've discussed, in 1936 the muon was discovered, a sort of short-lived heavy electron, in cosmic rays, prompting the famous response, "Who ordered that?" It turned out that there were lots of other particles that needed to be explained. In one area of physics, cosmic rays were being examined using cloud chambers. These cosmic rays are the subatomic particles that are constantly bombarding Earth from outer space. Many of them come from the Sun, but the origins of many others is still unknown. A cloud chamber contains supersaturated vapour. When a charged particle passes through, it knocks electrons off atoms, and the resulting ions, charged particles left behind when the electrons are knocked away from the atoms, well, they act as little nuclei that cause droplets of vapour to condense around them, leaving a track of clouds behind them. And these little trails, visible to the naked eye, but left by these tiny subatomic particles that you could never see, well, they have characteristic shapes that allow you to look at the cloud chamber and tell what's shown up. The heavy, blundering alpha particle leaves a short, thick, straight track. Electrons are lighter and less ionising, so their trails are thinner, and they're deflected more by collisions, electric and magnetic fields, as well as travelling further. These kind of experiments discovered all sorts of particles, including ones with the same mass of the electron that carried the opposite charge, the muon, and in the 1940s, weird particles called kaons and pions that no one quite knew what to do with. Physicists had managed to work out that alpha radiation was the same as a helium nucleus, and that what they'd called beta particles were electrons or positrons. But there were still some unsolved problems about the nature of beta decay. It seemed to the physicists that radioactive beta decay, which was observed in some unstable atoms, involved a change. A neutron emitted an electron and became a proton. But this couldn't be the whole picture because neutrons, when isolated, decayed themselves. We now know that neutrons are part of most nuclei. But when they were first discovered, it was as yet another form of particle radiation. This radiation was more penetrative than alpha particles, but didn't bend in magnetic fields. Physicists initially thought that it might be gamma rays, but it was later proved to be a new particle, the neutron. If you have an isolated neutron that's sitting more or less still, it decays with a half-life of 885 seconds. That means that if you have a pile of neutrons, on average, half of them will have decayed after around 15 minutes. When they decay, we can see protons and electrons emerging, but there is an issue with this picture. You can't have one particle splitting into two, and always conserve both energy and momentum. Remember that momentum is like a measure of how much stuff is moving in a given direction, similar to the mass times the velocity. Realising that you can't have one particle split into two and conserve both energy and momentum isn't so difficult. Let's say that we have a neutron sitting still and it splits into an electron and a proton. There's no overall momentum before the decay, the thing's just still, so there must be no overall momentum after the decay. This means that we need the final momentum of the electron and the proton to be equal and opposite. The problem is because the mass of the electron is just so different to that of the proton, there's no way to conserve energy and momentum with just two particles. The sums don't work out. But you can fix them if you have a third particle that's created in the decay, one that can carry off the extra energy and momentum. And this also explains why, when beta decay occurred, they could actually see a range of energies and momenta that came from the beta decaying particles. In fact, something else is being produced. That way you can get a range of different speeds, energies and so on that physicists have observed when neutrons are decaying. Enter Wolfgang Pauli. One of the giants of quantum mechanics, he was also famous for his acerbic personality. His colleagues coined the term the Pauli effect for his mysterious ability to break experimental equipment simply by being nearby. Pauli was a true theoretical physicist, and he loved this little coincidence. He was a perfectionist who had little time for anything he considered to be incorrect, which is the kind of attitude you can only really get away with if you are a genuine genius. But worse than things that were incorrect were those things that were so unclear they offered no testable predictions. For Pauli this was completely beyond the pale, outside of science, and for one paper like this, he offered the grim conclusion, it's not even wrong. Ouch. Now I didn't know this until researching this episode, but Pauli actually introduced the idea of the neutrino in a letter that began, quote, "Dear radioactive ladies and gentlemen." In this letter, written in 1930, he expressed hope that the physicists he was writing to would be able to directly detect the neutrino and confirm this theory, which makes sense. If it couldn't be tested, then it was not even wrong. In fact, when fellow physicist Enrico Fermi submitted a neutrino paper to Nature, arguably the most famous journal out there, they rejected it, saying that it was too remote from reality. Now you can see why people might be sceptical about the neutrino. After all, it seems very convenient that there's another particle that just exists to solve this particular problem, because they had this problem of beta decay, and just inventing another particle to solve your new problem might seem a little bit unnatural. Does it just exist to carry away excess momentum and energy and make our sums work? And it happens to conveniently be too small to be detected with current technology? You can see why people were sceptical. But Pauli was vindicated when the neutrino was observed in 1956, 26 years after he'd first posited it as an idea. It was just a couple of years before Pauli died, and he reportedly said, "Everything comes to him who knows how to wait." And then it took another 40 years to award the people who discovered the neutrino with a Nobel Prize, which happened finally in 1995, the year I was born. Those who can wait indeed. Neutrinos are weird. They are ghostly particles, incredibly difficult to detect. If you don't believe me, consider that right now, as you listen to this, 100 trillion neutrinos are streaming through your body. Yes, we did model you as a rectangle there, don't think about it too hard. Most of them come from the Sun, which rains down an astonishing 65 billion neutrinos on every square centimetre of the Earth, every second. But they're so reluctant to interact with matter that almost all of them pass straight through the Earth and flow out the other side. It used to be thought that they had no mass at all because they were travelling at almost the speed of light, so close to the speed of light that it's basically indistinguishable. And we know from special relativity that no massive particle can travel at the speed of light. Now we now know that they do have a mass, but it's really, really, really tiny. So tiny that all of the neutrinos that will pass through your body across the course of your life wouldn't weigh more than 1/1000th of a gram, and possibly much less than that. So how do you detect something whose gravitational influence is so puny that you'd never be able to find it, that can happily pass through the entire Earth without hitting anything or interacting with anything? Well, you get lucky. If you want to measure these neutrinos from the Sun, one of the methods is to use a big vat of water. 1,000 tons of the stuff was used at the Sudbury Neutrino Observatory in Canada. They actually use heavy water, which is slightly radioactive. Heavy water is like normal water, H2O, but the hydrogen is a different isotope. So isotopes are these. An isotope of an element is the same element, but with different numbers of neutrons in the nucleus. So normal hydrogen has just a proton in the nucleus, but in heavy water, with heavy hydrogen, the hydrogen has a proton and a neutron. And this is good for neutrino detection. See, what can happen, albeit with low probability, is kind of the opposite of a beta decay. So I like to think of the neutrino as a bit like the ghost of an electron, or maybe a sort of electron shell. A neutrino can interact with a neutron and turn into an electron, leaving a proton behind. So its neutrino plus neutron turns into proton plus electron. This is the type of interaction that rarely, but possible to detect, does occur in these huge vats of heavy water. It turns out that neutrinos can interact with electrons and nuclei, as well as via what's called the weak nuclear force. They're called weakly interacting for that reason. And as the name suggests, these weak interactions don't happen all that often. In particle physics, you'd say that they have a low interaction cross-section, which just means that the interaction is unlikely to happen. The reason I like to think of the neutrino as the ghost of the electron is that a neutron can pass something to it that turns that neutrino back into an electron. And similarly, an electron can lose something, a spirit and essence if you want to. And similarly, the electron can lose something, it can pass something to somewhere else, leaving behind the ghost, the neutrino. And of course, they're much like ghosts in the sense that they just continue to flow through solid matter without seeming to interact at all, except very, very rarely. So you might be thinking, if muons are like heavy electrons, do they have similar interactions? And yes, it turns out they do. Muons have their own muon neutrinos, which can be turned into muons through a weak interaction. And we're going to jump in time a bit here, but in the 1970s another particle was discovered, the tau particle. This has the same charge as the electron and the muon, but it's way heavier than both of them, and it's way more unstable. Electrons, essentially, as far as we can tell, live forever. Muons live for a couple millionths of a second. Tau particles live for less than a trillionth of a second before they decay. And tau particles have their own tau neutrinos as well. All of these particles are called leptons, and we call them the three generations of matter: the electron generation, the muon generation, and the tau generation. So you've got an electron, a heavy electron, and an even heavier one called the tau, and they all have their own neutrinos. At this point, you're probably beginning to see why everyone is saying, "Oh my god, who ordered that?" And you might be thinking, how do we know that the electron, the muon, and the tau are really it? How do we know that there aren't just heavier and heavier, and less stable particles, more generations of matter, forever? It's a good question, but we can be pretty sure that there are just three, because presumably, if there was going to be a generation of matter even heavier than the tau, there would need to be a pretty hefty neutrino to go along with them. And we've looked at the decays of heavy particles and found no such neutrino. CERN have said that there's a 99.99999% probability that these are the only leptons that exist. Although we should know by now that physics has a kind of a way of throwing up new and inconvenient particles just when you think you've got it all sorted out. So recap, here we are. 3 generations of leptons: electron, muon, tau, and then neutrinos. Oh, and I haven't mentioned it so far, but you've remembered that every particle has its antiparticle, right? Same is true for electron, muon, tau, and all of the neutrinos. They all have their antiparticles. Alongside the proton and the neutron, you're sort of starting to have a model here. But there are all of these weird kaons and pions to explain from the cosmic rays and the particle accelerator experiments that were starting to happen more and more in the 20th century. More and more particles were getting added to the particle zoo. The delta particles, the omega particles, the sigma particles. They were all incredibly unstable. They all had different charges, or they were always multiples of the electronic charge, and they could all be found in particle accelerator experiments, or sometimes cosmic rays, and it seemed like there was no end to them. In the 1950s, a physicist, Murray Gell-Mann, organised these into groups, and later he came up with a theory to explain these groups. Protons, neutrons, and all of these particles they were finding, they weren't really fundamental at all. They were made up of something else that was fundamental. Quarks. So a note on pronunciation. I'm going to pronounce it quarks, and this is correct, because he nicked the name from a famous doorstop and impenetrable self-appointed novel, Finnegan's Wake, which includes, alongside a whole bunch of other stuff, the phrase 3 quarks for Muster Mark. And unless you pronounce Mark as Mork, you can't pronounce quark as quark, or it doesn't rhyme. Now you might think that James Joyce didn't have a rhyming novel, in which case, say what you like. But I'm going to assume that he did, so there we go. So the quark model. The idea that all of these particles were being discovered were made up of something else. Well, it could explain a lot of the properties that were observed. Some of the particles they had seen decayed only via the weak interaction, and had slightly longer lifetimes, and they were called strange particles. So with the quark model, you could say, okay, all the strange particles have a strange quark. The quarks also need to explain the charges of the particles. Every particle discovered had some multiple of the electron charge, just like the proton. This unit of charge was thought to be fundamental. So then the quarks become really more of a maths puzzle than a physics puzzle. This is because the quarks weren't discovered in an experiment like other subatomic particles. Instead, they were proposed as building blocks that could explain the properties of the zoo of particles that had been observed. So to explain all of the charges, they needed to have an up quark that was positively charged, with a charge of 2/3, and a down quark negatively charged, with a charge of -1/3. The strange quark that was found in the strange particles needed to be negatively charged, with -1/3 as well. And all these quarks also had anti-quarks with their opposite charge. And this is really very similar to how the periodic table of the elements was organised. They were still discovering elements the whole time, so they hadn't quite filled out the table. They had a set of elements of various masses and charges, and you could explain them by considering a nucleus and saying, okay, the nucleus is made up of things that are this heavy and they have these charges. Organising the elements by their properties and their weights allowed the early chemists to spot the patterns and understand the rules that the underlying structure would have to obey. That's how they ordered the elements originally. And that's exactly what happened with the hadrons, the things that are made of quarks. Sorting them made it clear that there must be quarks, and it told us the properties that the quarks needed to have. And this was great, of course. Now you could see that the proton was made up of 2 up quarks and a down quark, which added up to 1. A neutron must be 1 up and 2 downs, which adds up to 0. Physicists quickly realised that the particles they'd been seeing were of 2 types. There were some which had 3 quarks, and these got called baryons. I have a joke with my physics friends, because we have no lives, that everything in physics is named after a guy called Barry. So, quarks were discovered by Barry Quark, electromagnetism was discovered by Barry Electromagnetism. It's an inherently comical name, sorry if you're called Barry. So I guess in this scheme, baryons were discovered by Barry Baryon. Some of these other particles, like the pions, could be explained if they were made up of a quark and an antiquark. These particles ended up being called mesons. And all of the particles made up of quarks together are called hadrons, because, particle physicists just love naming things. That's what they love the most. The great thing about the quark model is that you can basically calculate what other particles should be. You can say, okay, I think there should be a meson that is a combination of the strange quark and the anti-up quark. And there is. I think there should be a meson that is a combination of the down quark and the anti-down quark. And there is. But you're not going to be surprised to hear me say this. These 3 quarks were not the end of the story, and it turned out there was another generation of unstable heavy quarks, just like the case with electrons and muons. But the top quark is ridiculously heavy. It has the mass of an entire atom of gold, which is made up of over 100 up-down quarks. So these 3 quarks, people weren't sure what to call them at first, the heavier ones. They briefly went with truth, beauty, and charm, but only charm was charming enough to stick around. This charming quark. Truth and beauty ended up with the less poetic names of top and bottom. But at least you can see this way that the top quark is like a heavier up quark, and the bottom is like a heavier down quark. And that makes sense because their charges are the same. And somehow if you take something strange and make it way heavier, it's suddenly charming. Not sure if that works, but whatever. 6 quarks, and we don't think there are any more. So there are some rules for how you can combine quarks that I won't bore you with. But basically, for some reason, nature won't let us have charges that aren't multiples of 1 electron. So whatever combination you cook up, it's got to be +1, -1, +2, -2, neutral charge, that kind of thing. You can't have 4/3 or anything weird like that. So now we have another part of the standard model pretty much set up. Before we had our leptons, the electron, muon, tau, and their neutrinos. Now we see that the proton, neutron, and all the weird unstable hadrons like the pi and the k and the omega and the list goes on. There's octets and octets of them, there's loads. But all of those are just made up of quarks, the up, down, strange, top, bottom, and charm quarks. These can combine in groups of 3 to give you baryons, or you can have quark and antiquark to give you a meson. By the way, I can't resist mentioning this. Lots of mesons are bound up in bound pairs of quark and antiquark, so that they can be produced in particle accelerators like the Large Hadron Collider, and they show up at a specific set of energies. These particles, which live for a long time, are called quarkonium, depending on the flavour of the quark. So while charm-anticharm pairs are called charmonium, which sounds wonderful, bottom-antibottom pairs are called bottomonium, which does not sound so wonderful. With the quarks, we're nearly there, but there's a whole additional branch that we need to add to the family to get to the standard model properly nailed down. And then, my dear sweet children, after wading through all of this with me, we can finally get down to our beloved BDSM. But first, a little bit more about the quarks, because quarks are pretty quirky. They do have masses, but their masses don't add up to the things that they make up. So the mass of a proton is not the mass of 2 up quarks, plus the mass of a down quark. This is because mass is really just a form of energy, and quarks have some energy associated with them because of the force that draws them together, the strong nuclear force. And the strong nuclear force is really, really strong. It's so strong, in fact, that it's impossible to separate a quark from its fellow quarks. They love being together. They cling to each other. We think that it's physically impossible to see a quark on its own. If you try to separate them by applying some kind of brute force, you find that the energy required to do so is just a huge amount. And in fact, that energy is enough to create another pair of quarks. As you pull the quarks further and further apart, rather than getting a quark that's freed from its prison, the energy that you're creating literally produces 2 more quarks that combine with your existing quarks. Rather than producing free quarks, you've just made more hadrons. And this is why physicists can only really infer what quarks are like by bombarding hadrons. You can't ever get one in isolation. In the next episode, we're going to talk about the final components of the standard model, the force carriers. We've already discussed each of the 4 forces separately in this episode. Gravity, the weak and strong nuclear forces, and electromagnetism. It turns out that at least 3 of these have particles associated with them, and maybe they all do. We're going to get deep into the standard model and hopefully tie up all the loose ends, and then if there's time, we'll talk about BDSM. Thanks for listening to this episode of Physical Attraction. Remember, you can find us on Facebook at Physical Attraction, on Twitter at PhysicsPod, always very active there. On the Twitter, you'll find a link to the PayPal tip jar, where you can give us just the price of a cup of coffee for all of the many, many hours of entertainment and chat-up lines that I have selflessly bestowed upon you. If you ask us questions via Twitter, we'll answer them on a future episode of the show. If you don't want to fall into the horrendous mire of Twitter, then you can go to the website, www.physicspodcast.com. There you'll find we've got a contact form that emails me. It's very convenient. You don't even need to remember the email. You can comment on any of the episodes. You can donate to us there too, see our Patreon. Please rate and review us on iTunes, and I'll shout out your name on the show in response, because any ratings or review help the evil algorithms that now control the world notice us. And if there's nothing else that you do for the show to show that you've enjoyed it, please tell just one other person about the show. Because if everyone tells one other person and converts them into a listener, as we well know by now, in just a few months, there will be trillions of listeners to this show. Not just here, but across the universe, in different galaxies. It's like a physics pyramid scheme. And I think that would be just great. I'll see you next time. Until then, be kind to each other.